All right. Okay, so last class we talked about, we showed that really Boolean circuits are quite powerful. Yeah? Yeah, it should allow you to resubmit. Yeah. And so we saw that Boolean circuits are quite powerful, right? You know, they can compute any function. Any function you can imagine, you can lay down a circuit and the output is going to be the function that you desire. And in showing that, we also came across this idea of syntactic sugar. So what do I mean by that? It's the concept that, you know, once you know how to compute a function in some model, you can reuse it. Right? In many models that is true, and definitely so for Boolean circuits. So for instance, in our proof, we build these circuits for the simple E alpha functions, which were checking for equality. And then we use that, or used those to build our main circuit for any function. Okay. So these are called syntactic sugar in the sense that, you know, every time you write a program, you're pretty much using that. You use some library routines in a black box where you don't have to recode or recopy and paste all the text that you already written. Okay. So in some sense, this part is there for convenience. If we really wanted to, we could have gotten rid of that, but it makes everything cleaner, modular, and it's very useful for thinking about things. Okay. And what we're going to do today is, as I said, three very important ideas. One, which is kind of the seed for the other stuff that's going to come, is viewing code as data. Okay. So it's a very simple idea, but you know, given how simple it is, it has had a tremendous impact on all the stuff that we do today. And we'll use this to talk about two other stuff. So let me elaborate. So what do I mean by code as data, right? So it means you have your circuit, but I'm going to view the circuit was meant as a computation, right? It's trying to compute something, you give it some input, now it's going to give some output. But now I'm going to view the circuit itself as input to another program. So we're going to view code as data. Can you think of any program that you might have used which kind of has the same thing, where it takes kind of programs as input and does something with it? Compilers, yes. Anything else? Interpreters. Right, all of these, they're taking code, even a web browser, right? It's taking its input is the HTML code, which is a language, it's a program in HTML, and it parses that and then renders it. Okay? So what we're going to do today is circuit itself can be represented as a 0-1 star string. So this is going to be the main target for today. We're going to try and show this and then understand its implications. What this allows us to do is to view circuits as inputs. Once I know that I can encode or represent circuit itself as a binary string, I can feed it to maybe some other circuit. We said that circuits take binary strings as input. Now a circuit itself is a binary string, so I can do the same thing again. Okay, so this allows us to view circuits as inputs. Okay, and a really let's see, how do I start? Okay, this idea that you can take circuits as input is at the core of what we call general purpose computers. Okay, what do I mean? You take your laptop, it is not pre-wired for one specific program. Okay, it doesn't just do multiplication, it doesn't just do, you know, maybe addition, it doesn't just do matrix multiplication. It doesn't just do shortest path on graphs. You can run any program you want on it, right? And why can you do this? Because you can view a program as an input to another program which will do the execution, right? So computers that are not pre-wired for specific tasks. Okay, so in some sense, even if you have a circuit model, you can have one circuit which can simulate other circuits on your machine. And we'll see a more advanced form of this much later in the course when we talk about Turing machines and we build universal compilers and universal Turing machines. Okay, so to elaborate, let me draw some boxes. We're going to see how to represent circuits as strings, right? And hence as inputs. Okay, and this will lead us to two implications. One, is it will actually allow us to show a limitation of Boolean circuits. And as we'll argue later, it's not just a limitation of Boolean circuits, but of computation in general. Okay, meaning that we saw that Boolean circuits are quite powerful. They can compute any function that we want. But there was a catch in that. In that, the size of the circuit we were looking at was very huge, was exponential, n times 2 to the m, right? But we also said, if you have specific functions that you're interested in, like addition, I can lay down a circuit of linear size. Multiplication, I can lay down a circuit of quadratic size. But can I do this for all kind of functions? Can I do it for factoring maybe? Well, it turns out that some functions do indeed need exponential size circuits. Okay, so they are quite powerful, but at the same time, there are some limitations, especially in terms of efficiency. How big does your circuit need to be? That means there are functions on maybe like, let's say 40 bits or 50 bits, which cannot be written in like, 2 to the 40 size circuits, which is a huge number. Okay, and this is not just a limitation of our model; it's a limitation of any model that you can come up with, as we'll argue. And so, what this will lead us to is something else called the physical extended Church Turing thesis. Okay, we'll talk about that, whether this limitation, the fact that you need this exponential size things, is it really just about Boolean circuits? What if tomorrow I come up with some crazier model, let's say with maybe not NAND or not NOR, whatever crazy stuff you have? Can I do better if I come up with a better basis gates? Okay, and the other direction, what it allows us to do is to talk about universality in computation. Okay, what does universality mean? Universality just means that there's one circuit which, if you know how to implement, you can pretty much solve any computational problem. Okay, without taking into account the resources for now. So, as I said, these are very, very important ideas. All three of them, the fact that you need exponential size circuits, it's a very important lower bound. And there are $1 million for, if you can find an explicit function which satisfies this property, as we'll talk about much later in the course. The physical external Church-Turing thesis, this is, you can view as a law of nature, right? It's not like a mathematical theorem that we can prove. It's an observation about physical world. Just as conservation of energy, we think conservation of energy is true. In the same way, we think this hypothesis is also true. And then universal circuits, as I said, is at the basis of general purpose computers. Okay, that's a lot of build up for what's to come. But let's start at the basic thing that we want to show, which is to represent circuits as inputs, as strings. Any questions about the big picture? All right. So as a spoiler, one of the things that we're going to explore again and again in this course is self-similarity, right? You can view circuits as inputs and then inputs as circuits and so on. And what we're going to do is like somewhat circular, but not like fully circular, as we'll see. Okay. And one caveat. Remember, in the last few classes, we built this model of Boolean circuits, right? But we had three models. One was Boolean circuits, one was NAND circuits, one was NAND circuit programs. Okay? And we know that all three are equivalent to each other. If there is a size as Boolean circuit, that's pretty much the size 3 times S NAND circuit or a size 3 times S NAND circuit program. Okay? But for the discussions today, talking about NAND circuit programs makes things very cleaner, much cleaner. So we will work with NAND circuit programs. Okay, so we will view NAND circuit programs as a basic model of Boolean circuits. Even though I'm saying Boolean circuits, we're only going to talk about NAND circuit programs just because we know that all of them are equivalent. Okay. And as a further reminder, let's recall what NCPs or NAND circuit programs were. Okay, so what did we have? We have a sequence of lines, right? And each line is of the form foo equals NAND bar comma blah. Okay, so we just had a sequence of lines, temp1 equals NAND of x1, x2. And then so on and so forth. That's the only thing. And the number of inputs was n. The number of outputs was m. And the number of lines was s. Right? That's the size of the program. That's how many lines you have. Okay. Let's do one example of an NAND circuit program that we will revisit again. So the example that we're going to look at is the XOR function. Okay. So recall the XOR function, it's one if and only if there's exactly one among the two inputs that you have. Right. And here's a NAND circuit program for it. It's not important what it is, we'll just use it as an example. So don't worry about where I'm getting this explicitly from. Okay, I'm writing it down fully because we're going to translate it into binary string, and then we'll use this as an example for that. Okay. You keep computing NANDs of previous things, and you get the answer. Okay. some 4 lines, which I'm telling you will compute the XOR function. So the last bit y0 is actually the output. Okay. And we have to now map. So this is an NCP that computes XOR. And what is our goal? I want to map this circuit into a binary string. Suppose you have a 9-circuit program with S lines, N input variables, M output variables, what have you. How can I convert it to a binary string? How can I represent just as a binary string? Any suggestions? How can I map a circuit program, 9-circuit program, which has the sequences of lines in some succinct way to a binary string? Any suggestions? So what do I need to know for each line, right? So there's the left-hand side variable, NAND, and then the 2 variables that appear on the right-hand side. Okay. So in some sense, if I want to map it to a succinct representation, what can I do? Well, think about what we did in the first 2 lectures, right? So we said if I can find an encoding of a single thing, single item, then I can build encodings for lists of those items. Okay. So if I want to do something like that, what can I do here? What's one thing I could try? If I want to encode NAND circuit program as binary strings. Yeah?
Could we represent each line as like a 3-tuple?
Okay.
And create a prefix where it encodes that and then just concatenate all the encodes.
Yes, exactly, right? So each line here really is of the form variable I equals NAND of variable J and variable K. Okay, so in some sense, what I need to know is what is the index, what's the name, what's the label for the variable which is appearing on the left hand side, and what are the indices of the variables which appear on the right hand side. So in some sense, I can map each line to a triple of integers I, J, K. I tells me, okay, which variable is on the left, and J and K are the variables on the right. And then I'm kind of building a list of these things, right, one after the other. And if I can find an encoding of a single triple, then I can find an encoding of lists as well, right? So let's use that, but here things are even simpler, as we'll see. So there are many ways to do this, but I'm going to follow one approach, which is the one used in the text and which is, I think, pretty succinct. So what we'll do is, suppose you have a NAND circuit program with S lines, N input variables, M output variables, and let's say P is the total number of variables used by the program. Okay. So this is what we are starting with. I'm giving you an NAND circuit program which has S lines. It's using, I need to tell you how many input variables there are, how many output variables there are, and there are S lines. So based on that, you can see how many total number of variables you're using. So for instance, if I go back to this XOR program, how many variables are there in the entire program? Well, there are 2 input variables, 1 output variable, and 3 temp variables. So the total number of variables is 6, right? Okay. So what we're going to do is to somehow fix the numbers of the input and output variables and then of the remaining. So I'm going to imagine, oops, this should be a nice rectangle. I'm going to imagine that I make a list of 0 through t minus 1 corresponding to all the variables, but I'm going to put the input variables 0, 1, 2, up to n minus 1. Okay, I'm numbering all the variables and I'm assigning the first n names to the n input variables. If they are special, I'm just allocating, okay, number 0 is going to correspond to the first input variable, number 1 to the x1 input variable, and so on and so forth. Okay, and the last m I'm going to reserve for output variables. All right. Okay. So anytime I see a variable t minus 1 that corresponds to mth output variable. Again, there are lots of choices to make. Why did I put them at the last? I could have also put them like immediately following the input, right? That's also fine. Anything would work. This is the choice that you're making. It's some convenient way to do it. Okay. So variable t minus 1 means you're looking at the mth output variable. Variable t minus 2 corresponds to ym minus 2 and so forth. Okay. And then whatever is remaining, these are the temporary variables. Maybe let me do some color coding. Okay. So these are the inputs. These names correspond to outputs, and the middle ones to temporary variables. Okay. I need to split these t names in some way, and this is the one that I'm going to adopt from now on. All right. And after this, I'm pretty much done, because now I'll say each line corresponds to a triple ijk. That's it. So I'm going to write each line of the program as a triple ijk, where these numbers range from 0 through t minus 1. Okay. So as was suggested right at the beginning, I'm going to write down each line just as a triple. It has at most, we have total of t variables in total. So there's one variable on the left and 2 on the right. So those are going to be 1, 2, 3. Okay. So this is the left variable, and these two are the right variables. Okay. And then define the whole program. I'm going to represent as, I'll tell you what's the total number of input variables. Then I'll tell you what's the total number of output variables. Then I'll tell you what's the total number of variables that you have, including temporary variables too. And then I'll start writing down the list of triples for each line. So for instance, maybe the first line is, let's say 11, 1, 2. And then the second line is 12, 2, 11. And then maybe I have 1, 2, 3, and so forth. Okay. So this is the list of triples corresponding to the S lines. Okay, so each line is a triple, have S lines in total, so I'll get S triples. Okay, any questions about this? So let me summarize what we just did. So in summary, so formally, every NAND circuit program of S lines on N inputs, M outputs can be encoded as a triple. I mean, not a triple, but something like this, right? So N is the total number, input variables, output variables, total number of variables, and L is the list of triples. Okay, so a program from now on is just this sequence of integers, right? Now you can think the program was like you had a DAG and everything in the definition, right? But right now there is no directed acyclic graph or anything. I just have this sequence of triples which encodes the entire program. Any questions? Okay, so let's just do, just for concreteness, where did our XOR program go? Yeah, it's right here. Let's do it just for this program, right? So what will I have? Imagine we have these names for the variables, right? So the inputs are all the way to the left. So 0 and 1 correspond to there. There's only one output, so that's at the very end. And total number of variables was 6. So here would be temp 1, let's say. Temp 2 is 4, and then you have temp 2, 3. Okay. So the list of triples, the first line says assign temp 1 to NAND of x0 and x1. So what that means is literally you're just going to encode it as 2, 0, 1. The second line is going to be 3, 0, 2. The third line is going to be 4, 1, 2. Right? And the last one is going to be 5. Temp 2 is 3. Temp 3 is 4. 4, 1, oh yeah, 3, sorry. Okay? So this is the list of triples. Right? And then, so the program is just going to be, okay, let me not. So the program is going to be encoded as how many inputs do I have? 2. How many outputs do I have? 1. And how many total variables do I have? 6. And then this list. Okay. So the entire program, this lines of test has been mapped just to this sequence of numbers. Right. And once we have a sequence of numbers, we can map it back to binary strings just from what we did in the first few lectures. All right. Any questions about that? Okay. But let's be more concrete, because today we want to be a bit more specific about how you represent even this sequence of numbers as a binary string. because we will use the fact that the encoding can be succinct in some way. So here's a question. How long is this representation? Okay. In other words, if I want to map this list of numbers and everything to a binary string, how many bits do I need? What is the final length of my encoding going to be? Mm-hmm. Oh yeah, that's also true. I mean, we could avoid writing down instead of writing down 6, you can just write down 3, which is the number of temporary variables. Or if you want, you can even avoid writing 6, because you know that there are S lines and there are M output variables. So the number of temporary variables is somehow S minus M and things like that. But it's not going to cost us too much to do this, and it makes things a little cleaner for us. But you're absolutely right that there is some redundancy into this already. Okay, that's a good point. Okay, but we're not going to worry about this too much at this stage, because we're going to do something reasonably efficient, but not like the optimal way. Okay, so I want to map this to a binary string, so let's do some accounting, right? How big can the integers that you see here be? How many triples will you see, and things like that. So let me ask a series of questions, and hopefully you can answer them for me. Question 1. How many variables can there be? Okay, so I want a bound on how many variables you can have in terms of the total number of lines. I have S lines in the program. So what's the maximum number of variables that you might see? Any guesses? Just tell me a good upper bound. It doesn't have to be optimal, but there is some bound I can infer just based on the number of lines. Yeah? Yeah, so that's what we're going to use. So this is at most 3 times S. Each line, if you're really unlucky or whatever, there can be 3 new variables each line, and there are S lines. So the total number of variables you're going to use is at most 3 times S. Okay. So now we have this. Okay, let me change the color back. So what this helps us do is the list of triples in L, right? So we had I, J, K. We can assume that these indices range over 0, 1, 2, all the way up to 3s minus 1. There is some bound in the number of temporary variables, but I'm going to be a little lax and just assume that the bound is at most 3 times S. Okay. Is there a question here, or? And yeah, that's true. And the total number of variables is exactly n plus m plus number of temporary variables. Okay. So that means I can represent each triple using dash bits. So how many bits do I need to represent each triple if I know that each number is from the range 0 through 3 times s minus 1? How many bits do I need to represent a single number in this range? Well, let's say I use binary encoding, right? Yeah. Yes. So let me be more specific and say you need the ceiling of log of 3s many bits for a single number, and then I have to write down 3 such numbers, so it's going to be 3 times log 3s bits. Okay, so this is okay, let me, what do I mean by this? So the triple ijk is going to be mapped to binary encoding of I concatenated with binary encoding of j concatenated with the binary encoding of k. Okay, and I can, since I don't have to be particularly efficient, I'm going to assume that each one is of length exactly log 3s. Okay, so in some sense I'm maybe padding with some zeros, where I'm going to write 0 as a string of log 3s many zeros. Yeah.
Can you explain the upper bound of 3s again? Because like I get it's because like there's 3 variables in a line of code. Like, why would we have a new variable on the j and the k?
Yeah. So it could be less than 3 times s, right? But it's at most 3 times s. Make sense? So
does it valid have a new variable on the right hand side that was in a previous line of code?
If it's an input variable, in some sense you can have it, right? So for instance, I can say temp1 is NAND of x0 and x1. That's the first line. So in that sense, x0 and x1 haven't appeared in the previous thing because of the first line, right? So you could argue in some sense that that's happening there, but you're right. You can save something in the number of lines, but as I said, I'm going to be lax.
And then s is the number of lines.
S is the number of lines, yeah. Yeah, the total number of variables can be better. It's like n plus m times plus s minus t, but we're not going to be, fighting over those constants. Okay? That's a good question. All right. So I'm writing the triple as this, concatenation of this binary encodings of each number. So 0 is going to be a string of zeros. 1 is going to be a string of zeros followed by 1. I'm just padding so that some things become easier. Okay. Any questions about this? And since we know exactly the length of each triple, I can just encode the entire list using exactly that. Okay, so can represent the list of triples L with. So I'm going to write each triple exactly as this sequence of 3 times log 3s many bits. So the total number of bits used is going to be exactly s times 3 times log 3s. Okay. So each triple takes me log 3s, 3 times log 3s, and the total number is s times 3 times log 3s. And we could have used the prefix-free encoding and all that stuff. We don't really have to do that here because we know the length of the encodings exactly. Okay. Any questions about this? Yeah. Right. So the things that are not clear here, we yet don't know what is n, what is m, and what is t, the total number of variables. If I know those three, then I know everything. And I know how long a string I'm looking for. I know how big is S, and then I can start breaking it up into chunks. Okay, so that's a good point that we're not yet done, right? So to write down the program, if I tell you N, M, T, and L, I'm done. If I just give you L, you don't know what S is, so you don't know exactly where to break it up. But now if I tell you the total number of variables in N and M, you know exactly what's happening. Okay, so what do? We have to represent even these things. Okay, so maybe let me do something like this. I'm going to do the binary encoding of N, the binary encoding of M, the binary encoding of T, followed by the representation of L. Okay, so this is I want encoding of N, encoding of M, encoding of T, encoding of L. Okay, and for the first three things, N, M, and T, I'm going to use some prefix-free encoding of integers, right? So these use a prefix-free encoding of integers. Okay, any questions about this? The first encoded, and we saw that if I can encode one integer, I can encode a triple of integers. So that's exactly what I'm doing. I write down the prefix-free encoding of integers and then concatenate it with the encoding that we have for the list of triples. So this is going to be my final binary string representation of the program. Okay, and the book has a, if you go to the book, you can even play with some software where you can take an AND circuit program and it will map it to strings, just as we saw in one of our demos, right? You start with some encoding and then you can build encodings of lists of things, and this is something very similar. Okay, any questions? Yeah. So we were using, so this part was already taking 3 times S times log 3S. Okay. Oh yeah, that's a good question. So we had to answer that, right? So now we have an encoding, but let's check how big are these little pieces in front, right? Question: how big can N be in terms of S? How big can N be in terms of S? My claim is that N is at most 2 times S. Okay, because each input variable must appear in the program somewhere, right? So if the input variable is not appearing somewhere in the program, then we don't count it. Okay, so there's a question: why do we need the metadata in front? Okay, so that's a good question. I mean, in some sense, you could avoid using the metadata completely, but you still need to know how many input variables you have, right? Maybe you don't need to know how many output variables you have, but you at least need to know how many input variables you have, right? And that's the only reason. Because if I just gave you a sequence of triples, it doesn't tell you which is input and which is output. So somewhere that information should be there. And once again, we're not trying to find the best encoding. We're just trying to find something which is roughly in the same ballpark. Okay. So the number of input variables is at most 2 times S. Similarly, the number of output variables is at most 2 times s, and the total number of variables, as we said, is at most 3 times s. You could be using fewer variables, but these are some upper bounds. Okay, yeah?
Can you explain why L is not prefix-free?
Why L is not, okay, so you can, in some sense, it's already prefix free, but I'm saying we don't have to do this conversion that we did before, because we know each integer is exactly of length log 3s bits, right? If you pad things with zeros at the beginning and they're all the same length, they will automatically be prefix free, right? If I have two things of the same length, one can be the prefix of the other if and only they're exactly equal, right? Which won't happen because these are different integers. Okay, so I mean, knowing the length kind of simplifies it a little, but we could also, like, take any encoding and then convert it to prefix free and then do the thing for triples as we did before. Okay, that will also work. Yeah.
Then we encounter a new beam. You wouldn't know what S has to be, how long S is, so we don't know.
Right, so we can know S just from N, M, and P, right? Because S is exactly, T is essentially S minus N minus M. Like the number of temporary variables you'll have, each line, right? Either, so question, how do we know S? And I'm claiming, what is T? T is okay, because each temporary variable has to appear on the left once at the first time, right? And we know that there are S lines, and actually this should be S minus M, sorry. Okay, the number of temporary variables you're going to have is S minus M. You have S lines, so you're assigning S variables, and M of those are output variables. The remaining have to be temporary variables. Okay, but that's a good question. Again, this is not an important detail. If you're having trouble with it, not trouble, but like if it makes things even cleaner, we could just tag along S here too, right? We can just put S also into a representation. Is going to add one more integer, not too complicated for us. Okay, yeah. M is the number of outputs, right? So each output must be given some value in the program. Like there should be a line which says y0 equals something, right? So that means that maybe you're saying basically it has to be at most S. Yeah, it has to be at most S. That's true. Okay. Any other questions? Yeah, these are all excellent questions. So what have we done so far, right? And if I'm using prefix-free encoding of integers, how many bits do I need? I basically need a logarithmic number of bits, right? So here, can do prefix-free encoding with O of log okay, let me write it properly. Can represent an integer x in prefix free with O of log x bits. Right, so we saw this earlier. I can represent an integer in binary representation using logarithmic number of bits, and then I can convert it into prefix free with something like 2 times log x plus 2. I'm not interested in the constants. I'm just going to put O of log x. Okay. So this thing is recall. All right. So what's the summary of all of this? Okay, so summary, a NAND circuit program with N inputs, M outputs, S lines goes into a binary string. So we have 4 pieces here. The first number maybe uses some constant times log s many bits. The second number same, third number same, and then have a list of things, right? So it's going to be 3 times O of log s plus 3s times log 3s. Okay. So I'm mapping every program to a binary string, but the length is going to be some, this is not a 0, that's a constant. Okay, some constant times log s plus 3s times log s. Many bits. Yeah? Okay, so we have s lines, right? Each output variable should appear somewhere. So that takes care of m lines. The remaining lines on the left hand side, you should be assigning temporary variables. Oh, right. So you're saying maybe I'm reassigning the same variable again, then t could be smaller than s minus m. Right. Yeah. You're right. So, okay. So the question was, how can I infer S just from N, M, T, and L? Okay, and maybe let me just change the encoding a little bit. I'm also going to put S into the encoding. Okay. So I had 4 lines here. So I can add 4. Okay. So now there is even less ambiguity, right? I also have the S. So let me do. Okay, so I'm encoding N, M, the total number of variables, the total number of lines, and then followed by the list of triples. Okay. Again, there are probably better ways to do it, but we don't care that much about the efficiency. Okay. It's a good point. Yeah. We are seeing both now. We are seeing the total number of variables, which is t, and we're also seeing the total number of lines, which is s. Okay. Any other questions? But this is not going to change the final number of bits we are going to use, right? So instead of 3 here, I'll have 4. Okay. Which in the end is going to be dominated by this 3 times s log 3s, right? So essentially, the total number of bits I have is s times log 3s. Okay. So I have 3 times s times log 3s many bits, and plus some 4 times like 2 log s or 3 log s. So the total number is going to be dominated by the second term, which I can absorb into a constant and write big O of s times log 3s. Okay. All right. So let's take a 5-minute break, and when we come back, we'll see some interesting implications of this simple fact that every circuit can be represented by a string of length at most O of S times log S. Okay. And there's a question in the chat, is the prefix free encoding of integers? We use the one where we replace. Yeah, you could start with that. And I mean, it's not too specific. We don't have to be too specific because we're not using many properties of the prefix free encoding except that the number of bits is going to be constant times log x. Yeah, so we're going to use 2 times log x many bits. Yeah, exactly. And there was a question, why don't we need to make L prefix free if it's in a list? The only reason is that we know exactly how long are the integers that we're going to see. So in some sense, what I can do is I can take first log 3s bits, those are the first integer. Log 3s, the next log 3s, so the second integer, and so on and so forth. If you know the length of the encodings, then getting prefix free is somewhat easier. So that's what we're exploiting. Okay. I mean, even if you don't want to use that, we'll incur like, maybe just make it prefix free and then do the encoding for list. That's going to cost us a factor of 2, but either one will work. Okay. So the bigger picture that we should take away, there are many ways to do this, right? Again, as I said, there are many ways to do this. There's no one unique way. So we had to make some choices, and the choices we made led us to this bound. The number of bits that we need to write down the program is some constant times s times log 3s. And I can, there's a log 3s inside, which is kind of annoying. I can remove the 3 and put a bigger constant in front. That's also fine. 2 times s times log 3s is the same as, some bigger constant times s times log s. Okay. That's the simplicity of the big O notation, right? It makes writing some bounds easier. And so the theorem that we just showed is that any NAND circuit program of size S can be represented as a 0-1 star string of length at most a constant times S log S. Okay. And if you do the back of the envelope calculations and work through some numbers, which I don't want to do, you can end up with something like this, let's say. Okay. You can definitely maybe even not do 20, you might end up with 5 or 4. I don't care much about the constant. What we're going to do would work even if there's 100 here, it doesn't really matter. Okay, but I just want to take this constant 20 just to be specific. Any questions about this theorem? All right, so now that we know this, let's use it for showing our first lower bound. What is a lower bound? It shows a limitation on the power of your computational model. Okay. So let me scroll this. So the first lower bound. Part of my research is in showing lower bounds, so this is definitely one of the first that most people see. So what we're going to show is that there are some functions which cannot be computed by circuits of small size. That is, they do need exponentially many gates to compute. Okay. So to make this formal, let me introduce one definition. Okay. So the definition is size n and s. So this is meant to denote all functions on n input variables in only one output bit. Okay. Again, for concreteness, we are going to look at only one output bit. Everything we are doing could be made to work even for multiple output bits. But since we are just trying to show that there exist functions which cannot be computed, we can study only one bit. So n input variables, one output bit, and the number of gates is at most s. Okay, or the number of lines in your program. All functions on n input variables and one output bit that have a NAND circuit program of size less than or equal to s. Okay, take all functions which can be computed with at most s lines of NAND circuit programming, s lines in the NAND circuit programming language. Okay, make sense? And what we're going to show is that if I take s to be a small bound, then there exist functions which are not in this set. So for instance, if I take s to be maybe 100 n squared, right? Then multiplication would be in this class, because we said multiplication does have an efficient NAND circuit program. Addition may be just a linear. But how about exponential? Would that capture everything? So what is everything? Let me also denote a name for that. So let all n be all functions, okay? All functions on n bits. Make sense? Okay. And the first lower bound we're going to show is that unless you take exponential size circuits, you're not going to get all functions in your class. So a theorem is that all n is not in size, okay. Once again, the constant 40 is not important. This would be equally impactful and meaningful if I wrote down 100 there, but it's true with 40, so let me just stick to that. So what does this mean? For all n, this is true. That is, for every n, there exists a function f on n bits that does not have a NAND circuit program of size less than or equal to 2 to the n by 40 times n. Okay. So maybe let me just give myself more slack and say 80 times n. It doesn't matter. The constant doesn't matter, right? Because things are exponentially increasing. So the small number that you put in front is not going to be of much importance. What this is saying is that there are functions which require at least these many lines to be computed by an NAND circuit program. Any questions about this? And in comparison, what did we do earlier? Recall, we said that every function has a NCP of size roughly O of n times 2 to the n. Okay. So we showed that if you go to size n times 2 to the n, then you get all functions. But if you're below 2 to the n by 80n, then you do not get all functions. Yeah? Say that again, sorry?
This includes sign split, because if that is the case, then all functions, like all these functions, included in the size n, in that sense, that they all functions.
Right, right. So we are saying that all n is not contained in this size, in circuits of this size. Oh, maybe this is not clear. Yeah. It's not contained. Okay. Any questions? Any other questions? So in comparison, like, once you go to n times 2 to the n, you get everything. And they also said that the book actually improves this to some 2 to the n by n, right? So roughly up to a constant, you know exactly what you need in terms of circuit lines, right? So as we increase the size somewhere, maybe at 2 to the n by n, you can compute all functions. Something slightly smaller, you have a big gap. There are many functions which are somewhere here. Okay. Any questions? Okay. So this sounds like a pretty, remarkable statement, right? How can I show that there are functions which do not have any circuit of this size? So imagine, how can you rule it out? How can you rule out there being circuits of exponential size even? Turns out there's a cheap trick which makes it work. And any ideas how we can prove such a theorem? As a hint, we already did most of the hard work. If you were to show it from scratch, it's somehow like, okay, here's a function, and I have to tell you that there's no way to get a better circuit for it. That's much more difficult than what we're going to do. All we are saying is that there exists a function which cannot be computed. I don't know what that function is. Knowing what that function is a huge open problem, but we know, okay, here's a function which won't, there exists a function which won't have small circuits. How can I approach proving this? Okay, so let's see. Proof of lower bound. So what do we want to show? So we want to show that all n is not contained in size n of 2 to the n by 80 times n. Okay. Suppose as a contradiction that proof is by contradiction. Suppose that all n is actually contained in this. Well, what does this line mean? All n is contained in size 2 to the n by 80n. It means that every function has a circuit of size at most 2 to the n divided by 80 times n. And I'm saying this is impossible for some reason. Why? Any suggestions why? One set is contained in the other, and we want to get a contradiction to that. Yeah? Yeah, so it could have been for some complicated reason that one set is not contained in the other, but we are in some sense lucky. And there's a way to show this just by counting the number of objects in the two sets. Okay, so I have all possible functions here, and I have all possible functions which have circuits of size at most this much. What we're going to do is just count the number of functions, and it'll turn out that the number of functions is more than the number of possible functions that have circuits of this size, just because the number of circuits itself is going to be smaller than the number of functions. Okay, so idea, count sizes of the two sets. I mean, even if the sizes were actually comparable, it wouldn't have meant that you have this inclusion. But at least if the left side is bigger than the other, then you cannot be contained. Okay? In some sense, we are going to be lucky in trying to prove this theorem. So, question. What is the size of all n? What's the total number of functions possible on 2 to the n inputs? Let's think about it, maybe a little bit slowly. If I asked you, what's the total number of functions possible on 2 bits? How would you compute it? Well, let's think back to our truth table notation, right? Let's say, you had zeros. You had 0, 0, maybe 0, 1, 1, 0, 1, 1. Okay. So what's the total number of functions on 2 bits? Okay. I have 4 values that I have to specify, and each one can be any of 0 or 1. Right? Okay. I can say, okay, 0, 0 is 0, 0, 1 is 0, all zeros, that's one function. All ones, that's another function. I can come up with any possible 0, 1 sequence in these 4 slots, and that's going to define a function on 2 bits. Right? So the total number of functions on 2 bits is 2 to the 4, which is 16. Okay? All right. How about all 3? The same thing. I'll have 1, 2, 3, 4, 5, 6, 7, 8. I can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1. Okay, I'll just do. Okay. I have 8 possible strings, and for each one, I have to give a 0 or 1 value. Right? So there are 8 slots, and I have 2 options for each slot. Okay? So the total number of functions on 3 bits is 2 to the 8. Okay? So can you now tell me what's the size of all n? Generalize this. So we got 2 to the 4, which is 2 to the 2 squared. 2 to the 8, which is 2 to the 2 cubed. So all n is going to be? Any guesses? 2 to the 2 to the n. Right? It's a humongous number. But why is that? Well, the proof is kind of in the picture, right? If I want to write down the truth table, I have 2 to the n possible inputs that you can give to the function. And for each one, I have to specify, is it going to be 0 or 1? Right? So proof, there are 2 to the n possible inputs. For each, you have 2 possible outputs. Okay, so basically, if you had a truth table, you had 2 to the n rows, and you had to fill out whether you're going to put 0 or 1 and each of those rows to the right. Right, so you had 2 to the n choices to make. Each choice you had 2 options, so you get 2 to the n. Okay, so this is maybe the easier direction in some sense, but now here comes the more involved direction, which is to count this number of possible functions when you restrict the size of the circuit. So the next question is, how big is size n of s? So I want to count the number of functions on n input variables when you're only allowed n input variables that have a circuit of size at most s. How can I count that? Any ideas? How can I count? Well, in some sense, if I count the number of circuits of size s, then I'm done, right? Every NAND circuit program corresponds to one function of this. So this is equivalent to counting, or easier than counting, how many NCPs can there be of size s? You have n input variables, 1 output, and s lines. How many such programs can you have? Any ideas? Well, we are trying to count, right? Well, we can cheat a little bit. What do we know about programs of size s? Size less than or equal to s, right? So let's say take a program of size exactly s. Take a program P. We know that I have a mapping, I have a way to represent it as a binary string of length 20 times s log s. Right? So recall our theorem from before. We said every NAND circuit program can be represented as a binary string of length at most 20 times s log s. Right? So this representation kind of in an indirect way allows me to count the number of programs that I can have. Right? So what's the number of programs? Implies number of programs of size s is less than or equal to, it must be at most the number of binary strings of this length. Right? I have a mapping, I am encoding every program as a string of so many bits. So the number of programs must be at most the number of strings. which is 2 to the 20 times s log s. Okay. So we're getting this indirect way of counting the number of programs by first looking at their representations. We know that every program is exactly a string of so and so length. So one way to count the number of programs, which is again might be a lax way, is that the number of strings is at most 2 to the 20 times s log s. Any questions about this? Okay, so now we are basically done because I know the number of programs of size exactly s is this much. Yeah. Say it again.
The number 20 is just a constant.
It's just a constant, yeah. It's not that important, but the thing is, it's really the s log s that's going to be important. That's absolutely true. And instead of, I mean, sometimes it's easier to write it with a fixed constant. So instead of saying, okay, there is a constant b and so on, I'm just going to use 20 as a placeholder, really. Okay. So I know that the number of programs of size exactly s is this much. And so this implies that the number of programs of size less than or equal to s is, I could have a program of size 0, of size 1, size 2, size 3, all the way up to size s, right? So I just have to do some accounting, and each one, let me say, is less than or equal to number of programs of size 1 plus number of programs of size 2 plus so on. Okay. So I get number of programs of size s. All right. And I have a bound on each one. The number of programs of size 1 is, okay, 2 to the 1 times log 1. The number of programs of size 2 is 2 to the 20 times s times log 2, and so forth. Okay. So that means I get this is less than or equal to L equals 1 through s. I just have to add up okay. Any questions? So we got this power from our idea of representing circuits as binary strings. That gave us an easy way to count, to get an upper bound on the total number of programs. There are many other ways. You can, okay, go back and check, okay, I have this triple sequence of triples. I have s options. For each one I have, maybe s cubed integer. So the total number is s to the 3s. That's another way to do it. But as we'll see, this allows us to use it for other purposes. Okay. Any questions? I had this sum. If you just do some arithmetic, you can reduce it to say that this is at most 2 to the 40 times s log s. Okay. And don't worry, really don't worry about this inequality. Okay. If you want, you can prove it by various ways. You have to do some geometric progression and some computation, but let's not belabor that point. Okay. Any questions? So we know that the total number of circuits of size s or programs of size s is at most 2 to the 40 times s log s. Right. So the conclusion is so we know that summary size n of s is at most 2 to the 40 times s times log s. Okay. And why did we even try and compute this size, right? We were trying to compare the sizes of all n and the number of possible circuits of size at most s. So let's finish that argument. If all n is contained in this bound, this should in particular imply that the size of the left hand side is at most the size of the right hand side. If a set A is contained in a set B, A better have fewer elements than B. Okay? So this implies 2 to the 2 to the n is at most 2 to the 40 times s log s. Okay. If I take logs, this implies 2 to the n is at most 40 times s times log s. Okay. If I want to capture all functions, the size that you have better satisfy this bound. 40 times s log s must be at least 2 to the n. Okay. And you can do some arithmetic now. So our theorem was that if s equals 2 to the n by 80 times n, then you get a contradiction, right? That's what we are trying to show. So substitute okay, I'm just substituting things and now I'm at a contradiction because log of 2 to the n by 80 n is at most times n, which is 2 to the n by 2. Okay. Now I have a division by 80n that should only decrease. So log of 2 to the n is exactly n or at most n. So I get this part. Okay. Which is a contradiction, right? I'm saying 2 to the n is at most 2 to the n by 2, which is a contradiction. Okay. So a contradiction to what? The fact that, you know, what we assume right at the beginning, which is this guy. So if all n was contained in size n of s, for s which was 2 to the n by 80n, then we are getting a contradiction. Okay. So therefore, our assumption must have been wrong. Okay. Any questions about this? I know it's a long proof. Yeah. The last step, yeah. So yeah. So basically, log of 2 to the n by 80n, I'm dividing by this 80n, right? So I'm going to ignore that. I'm just going to say it's at most. So let me write it this way. I can say it's at most 2 to the n by 2 times n times log of 2 to the n. Okay. I'm only increasing and getting an upper bound, which we know is exactly equal to this guy. Right? So log of 2 to the n is n, and the n and n would cancel, and you'll get 2 to the n by 2. Okay? There was a lot of slack in the constants throughout. That's why we didn't pay too much attention to the constants. We could have done, the proof in many different ways. But the core idea was that if I know how to represent a circuit as a string in some succinct way, that allowed us to count the number of programs. Okay? Yeah?
So if we substituted s for 2 to the n over n, then we wouldn't necessarily have contradiction.
No. And in fact, we know that it is possible to get circuits of size exactly to, like in the upper bound is 2 to the n over n. So there's this fine trade-off, and we're hitting that bullseye exactly. Okay, that's a good question. Any other questions? Yeah?
Why did you substitute that to n over to the n over n?
Yeah, so that's kind of, I'm cheating, kind of going back in time, right? So if you go back to our theorem, so our theorem was that you do not have circuits of size 2 to the n by ATN. Right? So we are trying to show this statement. So the S that we're interested in was 2 to the n by ATN. Okay? So I kind of, why did I come up with this number? Because I did this whole proof before, and I knew what number to plug in at the end. Okay? You can also try and optimize here. So basically, the right trade-off happens exactly at something like 2 to the n by n. All right? Any other questions? Okay. So let's summarize. So what did we do? We started out with this idea 1, which is represent circuits as strings. Count circuits using number of strings. Okay? And then we use this to compare sizes of all n and size n of s. Okay? So all this is saying, we are doing a proof by contradiction and so on, is that there is some function on n bits which requires circuits or a NAND circuit program of size 2 to the n by 80 times n. Okay? And this will also imply something similar for Boolean circuits, right? Every Boolean circuit can be implemented by a NAND circuit program with a constant blow up in the size. So you can kind of translate from one to the other with some constant losses. Okay? But this doesn't tell me, like, if I give it an explicit function, it won't tell me whether that is going to require an exponential number of gates. And that's a huge open problem within computer science. And it's very related to the P versus NP question that you might have seen before. Okay, so let me end with one more remark, which is that same holds also for Boolean circuits. Okay, meaning if I replace this 2 to the n over ATN with maybe something like another constant 2 to the n by 300n or something like that, then I can get the same conclusion, but for the Boolean circuit model, where the gates are Boolean gates instead of NAND gates. Because we know that every NAND thing can go back to Boolean, and Boolean you can go back to NAND. Okay? And what we'll do in the next class is to take this idea further and look at its other implications. Representing circuits as strings, we'll devise universal circuits based on this. Okay? All right. So that's all for today, and I'll see you on Wednesday. And remember that assignment 1 is due today at 10 o'clock. Yeah? That's the next assignment is going to be released next Monday. If you actually go to the calendar, you'll see when each assignment is going to be out.